In this third and final video involving calculating volumes using cross-sections, we'll consider an example which makes use of the volumes of washers. So in this example, we'll consider the region R bounded by the graphs of y equals 2 times the square root of x equals 1, and the x-axis. Suppose R is revolved around the line y equals -1. And find the volume of the resulting solid. So as we did before, we want to draw a sketch of the region. So here I've outlined the region in black, and I've also indicated the axis of revolution. So this is y equals -1. Next, we want to draw a sketch of the three-dimensional solid that results. So here, I'm going to consider where each piece of the region R goes when we revolve it about the line y equals -1. So the first thing I'm going to do is I'm going to take the piece along the x-axis. So between 0 and 1, this segment, if it's 1 unit above the line y equals -1, when I rotate it, I can see that part of it goes 1 unit below the line y equals -1. So there I draw my segment, and then I can draw in the circular aspect of it. So this ends up producing a hole for my three-dimensional solid. This point, the point 1, 2, is 3 units above the axis of revolution. So therefore, as it comes around, it's going to go to the point 1, -4 and come back up around. And then this segment here, the segment for y equals 2 times the square root of x, is going to come down here. So there's an image of my three-dimensional solid that results. Okay? And you can imagine that as we make slices that are perpendicular to the x-axis, that those slices are going to look like washers. So that's what we'll do next. We'll partition the interval 0 to 1 because we're taking cross sections that are perpendicular to the axis of revolution. So the axis of revolution, y equals -1, is parallel to the x-axis. So we're going to partition the interval from 0 to 1 with x sub 0, which is 0, x sub 1, x sub 2, x sub k minus 1, x sub k up through x sub n, which is our right endpoint of 1. Okay. Now we've already drawn a sketch of the three-dimensional solid that's resulted, but we also want to consider when we partition this region using thin rectangles, what happens to a thin rectangle as it's revolved about the line y equals -1. So I'm going to take this kth rectangle and I'm going to rotate it about the line y equals -1. And I get that washer. And I'm going to come over here and work with it over here. And I'm going to mark it up with dimensions. So I'm going to transfer this axis this way. So here is y equals -1. And I want to consider the outer radius and the inner radius. Well, the outer radius is based on where the function is evaluated at the endpoint x sub k. So this top point is 2 times the square root of x sub k. I want the distance from 2 times the square root of x sub k down to -1. So therefore my outer radius is going to be the greater minus the lesser. So it's going to be 2 times the square root of x sub k minus a -1. So it's the top minus the bottom again. The inner radius comes from revolving the segment from the x-axis, revolving it around the line y equals -1. Here's where we have y equals 0, y equals -1. So that inner radius, which we'll denote as r sub I, is 0 minus a -1. So that inner radius has radius 1. I've got that the outer radius of the kth washer is 2 times the square root of x sub k plus 1. The inner radius is 1. So when I calculate the volume of the kth washer by taking the area of the kth cross-section times the width, I'm going to get pi times the outer radius squared minus the inner radius squared times the thickness of the slice, which is delta x sub k. So therefore the volume of the kth slice is pi times 2 times the square root of x sub k plus 1 quantity squared minus 1 squared times delta x sub k. I expand and simplify, and so that kth washer has volume of pi times 4 times x sub k plus 4 times the square root of x sub k times delta x sub k. I now want to sum the volumes of the slices to approximate the volume of the solid. So I'm going to sum delta v sub k, k going from 1 to n. I've got the Riemann sum, k going from 1 to n of pi times 4 times x sub k plus 4 times the square root of x sub k times delta x sub k. As the norm of the partition goes to 0, I get the definite integral from 0 to 1 of pi times 4x plus 4 times the square root of x dx. And again, the limits of integration come from the interval that we partitioned along the x-axis, resulting in evaluating pi times 2x squared plus 8/3 x to the 3/2 power from 0 to 1 to get 14 pi over 3 cubic units.